Okay, so adding elements to the binary heap. So today we're going to talk about we'll get to adding elements into the binary heap. But first, before there is some important terminology and concepts leading to that. We need to go over prior. So we want to look at some terminology and concepts before we talk about the adding elements to a binary heap. Okay, so the first thing is that a very popular way to implement a binary is a priority queue is to use some kind of heap. So this is because heaps are the data structure that give us the best possible time complexity for the operations we need to perform a priority queue. But uh, um, however, I want to make something a bit so now let's make it clear. So a priority queue is not a heap. Uh, so a priority queue is an abstract data type, and it could be implemented in a lot of different ways. For example, we can use a heap that just lets us actually implement the behavior a priority queue should have. And as an example, we can use, for example, an unordered list to achieve the behavior we want for a priority queue. But this would not give us the best possible time complexity. So it's much more effective to uh, use a heap instead of some unordered lists, etc. So now we want to use heaps here, but which type of heap? Because there are many types of heaps we could use to implement a priority queue. So, for example, binary heap, Fibonacci heap, binomial heap, parent heap, and so on. So here we want to use binary heap. So let's have a look at how actually a binary heap works. So the following is a binary heap because it satisfies the heap property that every parent's value should be so every parent's value is greater than or equal to the child's value, and that every node has exactly two children. Well, in this picture, in this slide, uh, there. So the bottom at the bottom node nodes at leaves, we don't have a children. So actually, uh, they have the children. These nodes have the children, but they're just not drawn. And these children are the null values. So they're not required. No, the null values are not required to have children. So we're going to omit these null values for simplicity, but also a important thing that binary heaps remark from complete binary trees that at every level except from the last is completely filled, and all the nodes are as far left as possible. So as you will see, when we insert nodes, we always insert them on the bottom row as far left as possible. So, uh, maintaining the complete binary tree property is very important because it gives us some kind of insertion point, no matter what the heap looks like. So that is important to have some insertion point, and with it we know how where do we have to insert new values. So here, in this slide, in this example, the next node will go to where this hollow circle is, and the next one to the right of it. So eventually we finish the row, at which point we needed to start a new row. Okay, and the last thing before we get into how to add values to our binary tree is we need to understand how to represent and construct one of the binary heaps. So, one of the most popular ways to represent a heap is by using an array, because of the complete tree property we talked about. So this is, however, not the only way to represent a heap. So a heap might be represented using, for example, objects and pointers, and recursively add and remove nodes as needed. But right now we're going to take a look at an array-based construction. So the left is the index tree. On the left is the index tree. So this just with 0 as a root node and the indices here. And on the right is the actual tree. So the left heap or tree, by the way, is needed to help you visualize the position of each node in the tree, and right tree is actually the actual tree. Okay. Also, as we read elements in the array from left to right, it's through pacing through the heap one layer at a time from left to right. Okay, so here in our tree, the element 9 at index 0 in the heap, so it's always at the top. So, for example, the 8 element is on the first index, and 7 is at second, and in this way we can assign the index to every element. So this way. Okay, and so now. And this way we can read the binary tree this way from left pacing from left to right. Okay, and the next interesting property that is, by the way, very important and a very neat thing, that storing a binary heap and array can be easily able to access, being able to access the children of a parent node using some formula. So let I be a parent node index of a parent node, and this means that the left child index would in the array and in the heap would be 2i plus 1, and the right child index, or the second child index, would be 2i plus 2. So that is in the 0-base system, and in 1-base we have just to subtract 1. Okay, now suppose we look at node 7 in the array. So it is being in this index is index 2. So our formula says that the left child of 7 should be located as 2 times 2 plus 1. So that is 5. And if we look at index 5, we get as expected 1. And the right child should be 2 times 2, or 2i, I is 2, so 2 times 2 plus 2, so that is 6. And we look at our array. If we look at our array, that gives us the value of 2. And that's right. If we look at the heap, that is correct, that the index of the left child of the 7 is 1, and the right child of the 7 is 2. And now let's want to know how to add nodes to a binary heap and maintain the heap invariant. So that is the most interesting thing here. How do we actually add them, maintaining the heap invariant? Because if we add nodes to our tree, but we don't maintain the heap invariant, that means that our binary heap is just useless. It can't be used in any way because there is just some tree with some elements. So let's look at some example. On the left, there are some instructions which tells us what value what values we need to insert into the heap, and the first value is a 1. So, by the way, if we look at the tree, the 1 is the lowest value. Every other value is less than 1, and that means it should appear at the root of the heap, since we deal with a mean heap. But instead of inserting 1 at the root directly and then try to rebuild the entire heap, we'll do this thing. We'll put it at the bottom left of the tree at the insertion position, which was the hello circle a few slides ago. So in this position on the left side, so that is also called, and so we'll do something that is called bubbling up, or so that is sometimes called swimming, or even sifting up. So all really cool. These names are for this operation. So operation is, by the way, very important. And now let's see how it works. So that is very interesting, I think. So we insert 1 at the insertion position and at this insertion point. And we are now in violation of the heap, since 1 is less than 7, and 7 is the parent node, and here we have a min heap. That means, so 1 is found below 7. So what do we need to do? And that is where it becomes interesting. We can just swap 1 and 7, and we're still in violation of the heap property, since 1 is a child of 6, but now with this thing with 7, with 1 and 7, we don't violate the heap, so we continue doing this. We swap 7 or 6 and 1, and yet again, in violation of the heap property, we need to swap 1 and 5 and its parent, and the heap property is now satisfied, so we are stop bubbling up, or whatever we can call it. So that is how we can actually add elements to the priority queue, and to the binary heap. And now let's look how to insert 13. So let's begin by putting at the insertion position, and then we're in evaluation of the heap property, since 13 is less than 14. Less than 14, and might be greater than 14. And now, one moment. Yeah, so 13 is less than 14, and 13 is a child node. So, now notice that we're no longer in violation, so the 13 is greater than 12 and less than 14. And that means that we have the correct heap, the correct binary heap. Okay. Now the next values are, we need to insert our 4, 0, and 10. And that's, of course, not the min heap, but the max heap. The elements at the root node is less than the element at the child node, for example. Okay, now let's look at where these will end up, 4, 0, and 10. And 4 goes at the insertion spot left of all the nodes on this layer, and we bubble it up until we can't bubble it up anymore. We don't need to. And here we continue bubbling it up, and that is we stop here because the heap property is satisfied now. And the same thing for 0. So of course 0 should be at the top of the tree, at the root node. So we're in violation of the heap property. Let's bubble it up. So we're continuing bubbling it. So here 0 is less than 1, so we swap them. And 0 is now at the top. Okay, and the last thing with number 10. So we insert it on the insertion position. And however, this insertion did not violate the heap because 10 is greater than 4. So we do nothing here. We just insert it, and now it's great. So by the way, that is the end of my talk for today. Thank you, Robert.
Yeah, very good. Yeah.